Hello, in this video I'm going to talk about characteristics of materials. Now to clarify, I'm going to talk about characteristics of materials related to stress and strain. There are many other characteristics and properties of materials that we are not going to talk about here, like electrical conductance and so on. So there are many other properties of materials, but here we're just really talking about stress and strain. All right, so strength of a material, that's the amount of stress and strain the material can withstand and still return to its original shape after the stress is removed. So essentially we're saying up until we reach the yield point and then enter the plastic region, the strength is essentially how big is that elastic region. So it's displayed by the elastic region. It's the area under the curve up until we get to the yield point. That's its strength. So if it can withstand a lot of stress, but very little strain, then it's not going to be as strong than if it can withstand a lot of stress and a lot of strain. Okay, so we're looking at the area under the curve that forms that elastic region. So like in the picture here, you could see the elastic region is very, very narrow. It's pretty tall, but very narrow. So this could be something like concrete, for example. Actually, concrete might even be more narrow because it really can't withstand any amount of strain before the material ruptures or fractures, I should say. Okay, tensile strength is the same thing, it's strength, but it's specifically referring to the amount of stretch that's happening in response to a tensile stress. So same thing as strength, it's just tensile strength. How much strength is there in response to a maximum amount of stretch? Ultimate strength is the amount of stress a material can withstand without failing, even when it causes permanent deformation. Okay, so ultimate strength is when we've gone past the yield point, we're in the plastic region, and then what is the point where the material fails? Okay, so like that's where the ligament ruptures or the bone breaks. So the point where the material fails completely. So that's the ultimate strength, is the area under the curve up until we get to that ultimate strength, up until we get to the failure. Okay, so yield strength is the amount of stress that a material experiences when it reaches its yield point. So at precisely the yield point, how much stress was that material experiencing? That's its yield strength. Failure strength is the amount of stress that material experiences when it fails. So when we get to that failure point, exactly how much stress was acting on that material when we got to that failure point. So the yield strength and the failure strength might be the same. So like with concrete, we're going to enter the plastic region and have a failure of the material at the same time when there's enough stress that it causes the concrete to fracture. So in that case, they'd be at the same time. But in lots of cases, we might reach the yield point where now permanent deformation is starting to happen in the plastic region, and that can happen over time before there's a failure of the tissue. So that's what happens a lot of times in the cases of tendon and ligament injuries. Is a lot of time there are repetitive stresses happening on those structures over time that are causing them to weaken, and then it takes one acute injury mechanism that then causes that tissue finally to fail. Whereas maybe a healthy tendon or ligament might have been able to withstand that force that was applied in that injury mechanism. We might have been able to withstand that if we had a healthy tendon or ligament. But because it has been continually deformed and broken down over time by excessive forces that put those structures into the plastic region, now it's failing at a lower amount of stress. So you can see that in this picture here is like we have that linear portion at the beginning, that's the elastic region. And then when it starts to curve, that's the plastic region. And you can see that that curve really takes a steep downhill towards the end there. And that's because as that material is continuing to deform more permanently, it's able to tolerate less and less stress without causing the tissue to fail. So that's why you get kind of that that downhill slope towards the end there of some types of tissue or some types of materials. That's not always true, but sometimes that's the case. Okay, ductility is the amount of stress necessary to deform a material. So ductility is really the slope of the stress strain curve, which we also refer to as stiffness. Okay, so the slope, the inverse of the slope is compliance. So any material we could say is somewhere on the sliding scale between very, very stiff and very, very compliant. So very stiff would be like concrete. Okay, so it can't tolerate very much strain, but it can tolerate a huge amount of stress. So it's very stiff. On the opposite end would be something that's very compliant. So it's very, very flexible and can withstand a lot of strain, but can be destroyed or fractured with a very, very low amount of stress. So any material is somewhere in that sliding scale with the two extremes, stiffness and compliance. So a ductile or pliant material is one that can cope with a large amount of strain but fails at low stress. So silly putty is a great example. It's very, very pliant, meaning that we can deform it to a significant extent. You know, if you've ever played with silly putty, you can stretch it and put in all different shapes, and it can be deformed to a great extent. But it only takes a little tiny bit of stress, a little tiny bit of force applied to the silly putty to be able to tear it. So it can't withstand much stress at all without causing the material to fail, but it can withstand an enormous amount of strain. Okay, so that means this is a very compliant material, but it's not a very stiff material. So a brittle or stiff material on the other end of the spectrum would be one that can cope with a large amount of stress and fails at low strain. So if it starts to deform at all, then it would cause the material to fail. So that's like concrete. So it's a very stiff material, can withstand a large amount of stress. It takes a huge amount of stress before we cause concrete to fail. But if the stress is sufficient to cause deformation, then the material is likely to fracture. So if the force is great enough that it causes the concrete to change in shape, which is the deformation or the strain, then likely that change in shape is going to be a fracture of the material. Okay, toughness. It's the total amount of energy required to cause the material to fail. So graphically represented by the area under the stress strain curve. It's a practical characteristic that takes into account its strength and ductility. Okay, so we're considering how strong is this material and how stiff or compliant is this material. So a material that is strong but brittle has low toughness. That would be like concrete. It's very strong. It can withstand a lot of stress, but it's also very brittle, which is another way of saying stiff, so it can't withstand much strain. So that means that it has very low toughness. A material that is not strong, like silly putty, but is very compliant, has moderate toughness, or we could probably also say pretty low toughness, moderate to very low toughness, just like the concrete. Okay, so silly putty also low toughness, or to moderate maybe. Okay, because it's not very strong. It can't withstand a lot of stress, but it can withstand a lot of strain. Okay, so it's very compliant. A material that is moderate in both, so moderate strength and ductility, has high toughness. So now we're saying that it has a moderate ability to withstand stress and a moderate ability to withstand strain, and that makes that material tough. So like in the bottom picture here, that red line is showing strong and brittle or stiff. The green line, weak and ductile. So that would be like silly putty. And then a balance of the two, that blue line, you see that we have a much greater area under the curve. That means that there's much more toughness. It's strong and tough. Okay, viscoelasticity. That's a characteristic of a material that causes its deformation or the strain to be affected by the length of time under stress and the rate of loading. Okay, so viscoelasticity means that the material, rather than us just saying, here's the amount of stress and that causes this amount of strain, we have to also consider the length of time that that material was under that stress and how quickly the time span that that stress was applied to that material. Okay, so any material that is viscoelastic means that the timing of this matters in terms of how much strain and how much strain is produced as a result of the stress, and if we reach our plastic region or our failure point. Okay, so viscoelasticity is a property that significantly affects the stress-strain relationship in that material. So most tissues in the body are viscoelastic. That's because of the fluids that make up a lot of our tissues. So like connective tissue, especially if you think about how our connective tissues are mostly gelatinous. Connective tissue is on a scale between an absolute liquid like lymph or blood and a solid like bone tissue or cartilage. And then it's on a sliding scale in between of like sort of a viscous gelatinous fluid. Some are going to be more liquid, less viscous, and some are going to be more viscous and closer to the solid end of the spectrum. Okay, so connective tissue, especially this is the case, where they are very viscoelastic, and these properties are going to matter a lot. So it's like tendons, ligaments, cartilage, bone, all of those are largely made of connective tissue. So there's going to be a very significant effect of their viscoelasticity on their stress strain relationships. Okay, so in bones, bones respond with increased strength and stiffness when loading rate increases. Okay, so what we're saying is that when the rate of loading, so we're talking about the speed, how fast the loading happens or the application of the force, when that force is applied more quickly, bones respond by being stronger and more stiff. So they're able to withstand more force and with less deformation. Now, to be clear, bones do deform as we load them. So like when we walk or run, you can, I don't want to say visibly see it like in a person, but if we were taking scans or something, we would see the bones, the femurs especially, actually bowing to a small extent. So it's not significant, obviously, because we would see everybody's legs bowing as they were running if that were very obvious. So it's slight, but there is deformation of the bones as we bear weight. Now, the faster we load them, so like the faster we're applying those forces, the stronger and stiffer the bones are in response because of their viscoelastic properties. Loading rates increase during running, causing greater strength and stiffness in load-bearing bones. Okay, so the faster we're loading the force onto the bones, the stronger and stiffer they are in response. In contrast, tendons and ligaments are a bit different. So other tissues like tendons and ligaments may be more likely to fail at higher loading rates. So at higher loading rates, which make bones stronger and stiffer, at those same high loading rates, those are the rates that are more likely to injure the tendons and ligaments because they don't become stronger or stiffer at a higher loading rate. So what that means is that the same injury mechanism may cause two different injuries depending on the loading rate. Okay, so at a higher loading rate, the bone becomes stronger so it can withstand more stress. So at a higher loading rate, we're more likely to injure a tendon or a ligament. So we might rupture that tendon or ligament that's undergoing that stress. Whereas if we had the exact same injury mechanism with the exact same forces applied in the same way to the same body, but those forces are applied at a slower rate, then it might be more likely to injure the bone instead of the tendon or ligament, because now the bone is not as strong when the rate of loading is lower. So in that case, the tendon and ligament would be a bit stronger, and those forces, the same exact force, but applied at a slower rate, would be more likely to injure the bone. So in that case, in that same exact injury mechanism, you'd be more likely to have an avulsion fracture, or an avulsion. So an avulsion is when a tendon or ligament rips off of the bone. And so that's really a failure of the bone tissue, because if the tendon or ligament fails, it would rupture the tendon or ligament. If the attachment of that tendon or ligament to the bone rips off, that was a failure of the bone. It wasn't strong enough to withstand the stress of the tendon or ligament pulling. So that was a failure of the bone. An avulsion fracture would be the same kind of injury, but now we've also taken a chip of the bone with us as that tendon or ligament ripped off. Okay, so same exact injury mechanism. If it happens faster, is more likely to cause an avulsion or an avulsion fracture, or both, I suppose. The same exact injury mechanism happening more quickly is more likely to make the bone stronger and will rupture the tendon or the ligament instead. So the length of time under stress also affects viscoelastic materials. So far we've been talking about the rate of loading, so how quickly that force was applied, but it also matters over how long is the tissue withstanding that force or that stress. So an example of that is in intervertebral discs. They're under stress all day long because of the compressive force of axial loading. What we mean by that is the axial loading is the weight of the body, so gravity traveling through the center of mass in the axial direction, so in the superior inferior direction. Of course, that's the direction of gravity. So that gravity, or the weight of the body against gravity, is causing compression stresses at every level of the vertebrae, every level of the spine. Okay, so that axial loading is causing deformation as the stress persists. So as we're still upright against gravity, that stress, that compressive stress, is persisting, and that's causing strain in the discs, or deformation in the discs. So that compression is like squeezing the discs and causing some amount of the fluid to leave the discs. And I'm not talking about a rupture. I'm talking about just a normal, like interstitial fluid that starts to leave the discs. So we lose some fluid that's squeezed out of the discs. And as we lose that fluid, it alters the disc's viscoelastic properties, and so the strain actually increases. So the more we lose the fluid as that compression is happening, the more deformation of the disc that happens as a result. Okay, so that's why at the end of a day, like if you've been on your feet all day and you're tired, and maybe you've been carrying things and working hard and all that, part of what's happening is that your discs are being compressed and they're being deformed. And then it feels so good when you finally get to lay down and be horizontal at the end of the day. That's part of what that relief really is that you're removing that axial loading, you're removing the forces that are compressing all the discs all the way up and down your spine. And so then you're removing that, the discs then can spend the night kind of returning back. They rehydrate and return back to their original shape. Okay, so the viscoelasticity in this case really matters, because we're saying that the length of time under stress going all day like that really makes a big difference. There's a very big difference between 20 minutes of axial loading and 18 hard hours of axial loading. Those are very different things. And so the reason that time matters is because the viscoelastic properties of the discs. Okay, creep. In the body, you'll also hear this referred to as tissue creep. So this is a material property that we could have of many different viscoelastic materials, not just in the body. And when it's in the body, we call it tissue creep. So it's the increasing strain that results from an unchanging stress in viscoelastic material. So when a stress is applied to a tissue over time, and maybe it's repetitively, maybe it's consistently all the time, like due to poor posture or something like that, it's the strain that continues to happen in those materials or in those tissues because it's a viscoelastic material. So it can be temporary or long lasting depending on the amount of stress and the length of time under stress. So I included this picture here because this is common. People sleep on their stomachs very often. And when you sleep on your stomach, there are a couple things that have to happen. You have to turn your head to the side so you could breathe and you're not just face down in your pillow. And you point your toes. You go into an extreme amount of plantar flexion because you need to be in that position because you can't just put your toes right through the mattress. Okay, so somebody who sleeps on their stomach very often will have pains, hypertonicities, postural dysfunctions, movement dysfunctions, things like that related to these exact issues. The head being cranked all over to the side and the toes being pointed all night long. So like when somebody comes to me with plantar fasciitis or plantar fasciosis, for example, and we'll talk about those later on, first thing I ask them is, do you sleep on your stomach? And that's because tissue creep happens when you sleep on your stomach and your toes are pointed like this all night long and night after night, for, 8 hours a night or however long somebody sleeps. What happens is you're in this plantar flexion. And so gastrocnemius and soleus that come together to form the calcaneal tendon and the insert in the calcaneus, they're in a shortened position all night long, every night, because you're in plantar flexion. And so that tendon will actually begin to creep. It'll begin to shorten and shorten over time. That's tissue creep because it's a viscoelastic material. So when it's in that shortened position all the time, at least, during sleep repetitively, it will become shorter and shorter. And as it does that, it's pulling harder and harder on the plantar fascia on the bottom of the foot. So it's putting more and more tensile stress on the fascia on the bottom of the foot because that tendon is pulling and applying more pressure to that fascia because it's all attached at the back of the calcaneus. It's all attached. So hypertonic or shortened calf muscles are going to put a lot of tension on the fascia on the bottom of the foot. And so that tension is now causing more tissue creep on the plantar fascia. So now that plantar fascia is deforming because it's also viscoelastic. So it's undergoing strain that's ongoing for a long time if you're sleeping on your stomach like this all the time. So it's deforming that tissue, and that can be very painful. It causes a lot of pain in the bottom of the foot. So like if somebody has plantar fasciitis or plantar fasciosis, you ask them, when does it hurt? If it hurts first thing in the morning, like they complain that when they put their foot down on the ground when they wake up in the morning and that it hurts so bad and then it kind of loosens up a little and feels a little better after that, it's how they're sleeping that's causing it. Okay, so things in general should feel better after we get up from sleep. And then if it gets worse over the day, it's something we're doing during the day that's causing it. But if it feels worst when we wake up in the morning and then feels better during the day, then it's something we're doing while we're sleeping, which for a lot of people is sleeping on their stomach in this position, causing tissue creep. Okay, so that is all I have for you in this lecture. And thank you for watching.